So good morning, everyone. First of all, I would like to thank the organizers for giving me this opportunity of talking to you about the emergence of galaxies in the first billion years. And what I was really hoping to do is just show you the implications of these, not just for galaxy formation, but also for cosmology, gravitational waves, and for reionization. And I would also like to start by apologizing to all of you for not being there in person, but it was a bit unavoidable because of personal circumstances. So thank you very much for putting up with the remote talk. So let me start by thanking the theory team here in Groningen, which was composed of young undergrad and master students, PhDs and postdocs who have really put together the work that I'm going to show you today. And I'm also showing this on behalf of a number of teams from ALMA, James Webb, SKA, and Euclid. So I think I don't have to tell this audience that the past few years have been really revolutionary in terms of trying to understand the early galaxy population. And especially with instruments such as ALMA and James Webb, for the first time, we're in a position of actually answering questions such as what were the physical properties of these early galaxies? How were these properties dependent on the environment? When and how did these galaxies actually reionize the universe? So which were the key sources of reionization? And what was the effect of reionization feedback back on galaxy formation? As we have heard, James Webb has been yielding a huge number of black holes, which naturally raises the question of, so what exactly are these black holes doing in terms of not just galaxy formation, but also for reionization? And we cannot grow these black holes, as I'm going to show you in a minute, without efficient mergers, which naturally raises the question of how many event rates are we actually going to see from these early objects with VISA. And something that I would also like to talk about very briefly is how we can actually use these galaxies as probes of the nature of dark matter. So here I'm going to talk a little bit about warm dark matter. So let me jump into the first part, which is really to try and understand what these early galaxies imply for galaxy formation and for cosmology. So we've heard a number of excellent talks which have already given us a really nice overview of these early galaxies that we have been detecting. And what I would like to talk about now is this overabundance of bright systems, which was one of the first results that came out with the James Webb. So here, what I'm showing you is the UV, the ultraviolet luminosity function, so number density of galaxies per co-moving volume as a function of the UV magnitude. And here are some of the earliest results from the James Webb. So here you have a galaxy at a redshift of 16.5, which was the highest redshift source that was proposed. And we also have these galaxies such as GNZ11 and a few galaxies here, which together make up the luminosity function at a redshift of 11. Throughout the talk, I don't want you to focus on any one specific model, but what I'm going to just show you is a suite of different kinds of models ranging from semi-analytic to purely analytic, abundance matching, etc. So here, let's start with the luminosity function at a redshift of 11. These are the observations and what theory is predicting. So these are theoretical models fully baselined against the data up to a redshift of 10. So this is all the data that we had pre-James Webb. So here, the luminosity functions that we had from these models are this solid grayish line, which is from the universe machine, this solid light gray shaded region, which is from the Delphi semi-analytic model. As you can see, none of these models were predicting galaxies as bright as GNZ11, which we were observing. The situation was even worse at a redshift of 16.5, because here what theory is actually predicting is these dark grayish, blackish lines that you can see here. So basically, theory was not predicting any objects like the ones that we are observing here. And remember, these are really small volumes. So of course, theoretical models were not working, so we went back to analytics. So here what I'm showing you is this dotted line, which is taking a halo mass function at a redshift of 16.5, assuming a cosmological ratio of baryons to dark matter and allowing all of those baryons to instantaneously form stars. This, you might say, is really the theoretical ceiling that is allowed in the lambda CDM cosmological framework. And you can see this redshift 16.5 source actually hits really well against this upper ceiling. So this was one of the first problems that emerged. So of course now the idea was to really try and confirm the redshifts of these objects. So everything that I showed you was purely photometry based. With spectroscopy, people made this enormous heroic effort. And here, for example, I'm showing you the spectrum of a redshift 11.4 source. So this is Macy's galaxy from Steve. You can see spectroscopically, again, matches the photometric redshift, the same thing for another redshift 11 source. But for the redshift 16.5 source, so this is work from Pablo Arabalharo, what he was basically showing is that spectroscopically, there are extremely strong emission lines from N2 plus H alpha or 3 plus H beta, which enter really specific filters, which are really biasing the inferred photometric redshift. So spectroscopically, this galaxy lies at a redshift of 5, raising the issue of whether this is really a pathology or if we should really expect a significant number of high redshift galaxies to have extremely strong emission lines, raising the issue of how well do we actually trust our photometric luminosity functions. So the situation has not improved in the sense that if you look at luminosity functions at redshift 12 and 14, again, these are really these are really over-predicted as compared to what theory was predicting. So here, for example, at redshift of 14, again, the observations that you have here photometrically, the luminosity function is actually approaching this upper ceiling again, 100% conversion efficiency of baryons into stars. And so a number of solutions have been proposed by the people actually in the audience there, ranging from the effects of dust really decreasing as you go to high redshifts, an evolving initial mass function, bursty star formation, maybe even a contribution from high redshift black holes, which could be affecting especially the bright end of the luminosity function, extremely efficient star formation, which could be feedback free, or low redshift interlopers, or a combination of all of these effects to different degrees. So for example, here, if you assume an evolving IMF, this has been touched upon already, as you go to high redshifts, these galaxies are not metal poor, but they're also not extremely metal rich. And so in principle, the initial mass function can be flatter than the typically assumed saltpeter or Chabrier initial mass function, which in principle, so if you look at the yellow line or the green lines, these are different kinds of evolving initial mass functions. So you are able to reproduce these extremely bright objects, which we could not with standard initial mass functions. You can also go for the fact that actually these galaxies are extremely bursty in terms of their star formation. So the galaxies we're observing could be extremely biased, and they could lie significantly above the typical star formation stellar mass relation. And if you actually allow them to vary by a factor of 5 or 10, this is the dark or gray shaded region that I'm showing you here. So in principle, you can actually explain these galaxies with the caveat that these are then not typical galaxies which are lying on the star formation rate stellar mass relation, but these are significantly biased in terms of their star formation rates. Now, what I would very quickly also like to do is show you that these early galaxies can also be used as excellent signposts to test the nature of dark matter. And so I'm not going to go through this in any great detail, but the idea here is really simple. So this was actually initiated by 2 undergrad students. So if you look at the standard cold dark matter paradigm, basically halos can form on all scales. If you invoke something which is light, warm dark matter, so of the order of, let's say, 3 keV, so this dark matter would have a higher velocity naturally than the standard cold dark matter paradigm, which means that if you look at the assembly of high redshift sources, a lot of halos that would form in CDM are not going to form in the 3 keV model, which basically means that you are going to delay structure formation to later redshifts or to later cosmic times. If you invoke something which is even lighter, so a 1.5 keV model, structure formation gets even more delayed, wiping out even more structure in the at really early cosmic epochs. So here, this is a really analytic calculation that we did as an illustration of the power of James Webb to shed light on the nature of dark matter. So what I did was I took halo mass functions in these 3 different cosmologies, so CDM, 3 and 1.5 keV warm dark matter. I looked at volumes of 10 to the 3 co-moving megaparsec cube, and for each halo, I assigned it a cosmological baryon to dark matter ratio, allow all of those baryons to form stars, which gives you the maximum stellar mass that you are going to measure in any given cosmology. This is plotted as a function of redshift. So what you can clearly see here is that in CDM, which is the black line, structure formation continues out to redshifts of even 25. So in principle, you would always have some amount of stellar mass if these low mass halos can form stars. In the 3 kV model, structure formation basically in these tiny volumes cuts off at a redshift of about 18. But if you go to really light warm dark matter models, 1.5 kV, structure formation is basically kind of shutting down at redshifts larger than 12 in these tiny volumes. Here, I'm also showing you the stellar masses that we have already measured from the James Webb. So you can see these are already hitting out to redshifts of 10 or 11. So a redshift of 12 is not very far off. And so the idea here is really simple, that if you could survey multiple blank patches of the sky with the James Webb, then in principle, if you start to see any bound mass in multiple regions to account for the fact of cosmic variance, in principle, you could easily rule out light warm dark matter models like 1.5 kV. And this is an epoch that we can really not access by any other means, highlighting the power of James Webb to also help us in terms of the nature of dark matter, which is one of the key outstanding questions in cosmology. In the interest of time, I'm not going to go into the details, but there have been a huge number of alternative probes of dark matter, which have been offered by the high redshift universe, going from 21 centimeter statistics, gamma ray bursts, direct collapse black holes, metallicity enrichment of the IGM. And I'm super happy to discuss this more later. But now what I would like to do is very quickly talk about the black holes that we are detecting at high redshifts with the James Webb. And I think this is something that has already been touched upon. The fact that we're detecting extremely obese black holes at high redshift. So here I'm showing you a compilation of the black hole masses as a function of redshift. These are all black holes that have been confirmed either spectroscopically or through X-rays or extremely high emission, high ionization emission labs. So now, again, analytically, you can explain most of these black holes, so 26 of these, you can explain with low mass seeds, so 100 solar masses from metal-free pop-3 stars, which are continually accreting at the Eddington rate after having been seeded at a redshift of 25. There are a number of outliers which are extremely massive. So for example, at a redshift of 10, you have black holes which already have a mass of the order of 10 to the 8 solar masses. If you want to explain these with low mass seeds, you need extremely high Eddington fractions of the order of 2. You can go for heavier black hole seeds, so 10 to the 4 solar masses, who again with an Eddington accretion rate can explain 32 out of these 34 objects. These two outliers require an Eddington accretion rate of 1.4, or you could invoke extremely heavy seeds of the order of 10 to the 5 solar masses, which accreting at the Eddington rate continuously after having been formed up to a redshift of 25 are able to explain all of the objects we're seeing. So as of now, we're in the situation that we either require extremely heavy seeding mechanisms to explain these enormously obese black holes that we're detecting at high redshifts, or extremely high Eddington accretion rates. The problem is compounded by the fact that we're also detecting an overabundance of black holes. So here, this is again the number density of black holes as a function of their bolometric luminosity. In the left panel, redshift 4.5 to 6.5, right panel 6.5 to 8.5. And all of these, the red points that you see are the black holes that have been spectroscopically confirmed with the Uncover survey. This is work led by Jenny Green. And if you compare these in the left panel to the Shen observations, you can see these are a specific class of black holes, little red dots, extremely overnumerous compared to what we were expecting from pre-James Webb estimates.
Sorry, Pratika, you probably can't see me, but I'm standing up to indicate that you
should
wrap up in a minute or so. Yeah.
Oh, wow. Okay. Yes. Okay. Very quickly, so you can see that there's an overabundance of black holes at high redshifts, and in principle, these are hitting again against this upper ceiling, especially at high redshifts, where you need each black hole to accrete continuously at the Eddington rate with a duty cycle of 1, which is really posing a problem for theoretical models. I'm just going to then end with this slide to show you that these black holes, so to show you the impact of these black holes for future observations with, for example, LISA. So this is as a function of redshift. I'm showing you the black hole masses. Each of these dots that you see are pre-James Webb black holes. And we were always invoking low mass black hole seeds to explain these light black holes we see at low redshifts. We needed heavy seeding mechanisms to explain high mass black holes at high redshifts. LISA is going to detect mergers between 10 to the 4, 10 to the 7-ish solar masses at redshifts above 2 or 3. And the black holes that we're getting with the James Webb lie in a completely new part of the parameter space. And so this has now really led to the question of what do we need to do to grow these enormous black holes? Because even as we speak, even pre-James Webb, the number of gravitational wave event estimates that we have for LISA vary over orders of magnitude. And now if we have black holes in a completely new part of the parameter space, the question is, how many event rates should we actually expect from the high redshift universe? I'm going to jump over reionization and just leave you with my ending slides. And if you're interested in talking more about reionization, then please let me know. And I will end here. Thank you.
Thank you, Pratika. Aklant?
Hi, Pratika. Thanks for a great talk. So you talked about different alternative dark matter scenarios, and you focused on these warm dark matter scenarios which suppress galaxy formation compared to CDM. But given that we almost encountered galaxies which we were worried that would break CDM, are there any dark matter scenarios you would consider which could potentially enhance structure formation compared to CDM, should the need arise in the future?
I think that is such a good question. Can I actually go the other way and go along the direction of what Caitlin was telling us about, which is that these stellar mass estimates remain really uncertain. So for example, there's been a huge amount of effort to show that if you would invoke a slightly different initial mass function, or if you would count for cosmic variance, then the stellar masses of these things could easily be lower by a factor 10 to 30 even. So I'm not sure we are really in the situation where we are breaking lambda CDM. But to answer your question, yes, there have been works where people have invoked different kind of dark energy models to actually increase structure formation at early redshifts, which in principle can allow you to assemble these extremely large masses at high redshifts if the need arises. Sorry, does this sort of answer your question?
I think we have a lightning talk on that topic, so stay tuned for that.
Hi, this is Alex G, University of Chicago. I'm wondering about the dark matter constraints as well. So from the low mass galaxy count side, we've sort of put limits on, the dark matter particle being above, if it's a warm particle, it's above 6.5 keV. Is there a regime where JWST sort of provides unique constraints compared to something like that?
Oh, Alex, what a good question. Okay, so I would argue that basically, if you look at the lamina of a forest, as of now, the constraints range between 2.3 to 3.3 keV, depending on what you do with the temperature density relations at these epochs. And so I would argue that really this is an unknown. We don't know what the temperature of the IGM is at a redshift of about between 2 and 4, given that this is the epoch of helium reionization. So in principle, the constraints that I would go for right now are of the order of 2.5-ish and above keV in terms of the warm dark matter particle mass. So I think these constraints that in principle we can find are really comparable. And I think the key point is that these are constraints at an epoch that we can't get a handle on the dark matter particle mass by any other means except for maybe 21 centimeter. So perhaps, as of now, this is really just illustrative. But I'm not sure if we can somehow break the degeneracy between the assembly of dark matter and the baryonic assembly. Then maybe we could extend these constraints to higher masses.
Further questions or comments? So Pratika, I actually had a question also about the work you presented on the warm dark matter. So you mentioned that those boxes are quite small, and I don't know if you were listening in to Chris Lovell's talk, but he was pointing out that you actually need, sort of more than 100 cubed megaparsec volumes to really come close to sampling the most massive halos. So are you concerned about that, or did you somehow estimate the effect of the volume on that calculation?
Oh no, this is, Rachel, what a good question again. So this is purely analytic. So all I'm doing is working with halo mass functions this is basically taking the power spectra in different cosmologies and saying what halo masses would you go up to in a given volume. So you can do this for any volume basically. And the whole point was that you would need to do this over multiple fields really to account for cosmic variance. So yes, now completely agree with you. But this is mostly an illustrative example of the maximum masses that you could go for. Of course, they will be much lower because of the effects of feedback, of inefficient star formation, etc. Sorry, does
Okay,
this
great.
sort of answer your question?
Yes, yeah, thank you. No, I understand when you do a first look, sometimes you have
Yeah.
to neglect some of these effects. I recommend to you very selfishly a paper led by Christian Jesperson, which Chris Lovell was also involved
Sure,
with,
of
where he
course.
looked into the impact of cosmic variance on this maximum mass
Yes.
estimator.
Yes.
Okay, I think that's our timer. So thank you again so
Thank you
much,
very much.
Pratika, for giving us that
Thank
lovely
you.
talk.